Hello, welcome to part two, or what would be day two on a normal year that's not 2020 of vector fields. So we talked today in class, Monday the 7th, we talked about what a vector field is, how to graph it, and how to find the potential function, tell if you have a conservative vector field. So this video is all about two ways of describing vector fields. And I'll kind of give you a quick summary here at the beginning. It's all about dot product and cross product. So we're going to see how that is, how we describe these vector fields using that. Okay. So here's the two ways we describe a vector field. The first one is called divergence, which is different from when we learn about this in Calc 2. We're talking about series and sequences. So divergence is the first one, and curl is the second one. So again, this is all going to go back to dot product and cross product. We'll talk about those second. First, we're going to talk conceptually about what divergence is. So divergence, starting there, is the measure of how much fluid or flow enters a region R compared to how much leaves. So I told you that we would talk a bit about water flow. This could be electricity, this could be energy, gravitational pull. Divergence is how much of it is entering versus how much of it is leaving an area, and specifically around a certain point in your region. So if more is entering, if more flow is entering the space than leaving, divergence is negative. So when we calculate divergence, it would be less than 0. And again, I'll tell you in a bit, how do we calculate it? So if divergence is negative, then we have what could be considered a drain. So if you're thinking about water flow, a drain in a shower or a bathtub or a sewer drain or something like that, there's more entering than leaving. So that's a drain. And in that case, divergence is negative. If the same amount is entering as leaving, then divergence is 0. You have this balance, so divergence is equal to 0. We call this divergence free. So in fact, we are free from divergence because this is flowing freely and there's the same amount of flow going in as out. And then if you guessed it, the last part of this is if more is flowing out than in, divergence is positive. So when we calculate divergence, it's greater than 0. And we have what's called a source. So when you have a source, there is more flowing out from that source than in, and divergence is positive. So that's conceptually what is happening with divergence. So how do we find divergence? Well, I told you kind of up front, this has to do with dot product or cross product. And in fact, when we're finding divergence, we are using dot product, which makes sense because we want a scalar. We want a scalar answer. So this really comes from the dot product, and we call this a specific operator del dot. It's because this delta here represents the gradient. So we call this del dot because we are dotting that with our vector field F. So if you think about taking a dot product, again, here we have the gradient. So the gradient of F looks like all of those partials. We are dotting it with our vector field F defined by functions m, n, and p. And if I take the dot product, what I am doing is I am multiplying these corresponding coefficients, and then I am summing the result of all of that multiplication. So what I'll have, if I take f partial x dotted with m, I am technically taking m partial x. And when I do the same with n, it's getting dotted or getting multiplied, sorry, by f partial y. So I'm taking n partial y. And then if this is in 3 dimensions, we would have p partial z. And like any dot product, we sum those together. So this mathematical operator here says to take m partial x plus n partial y plus p partial z, and that is the equivalent of taking del dot f. So there is dot product at the root of this, but you are not actually sitting and calculating the dot product for two vectors every time you do it. If you have your vector field F, you are essentially doing this operation here. So let's go ahead and do an example of that to find the divergence at a point 2, 1, -1 for our vector field F. We want to calculate our del dot operator. So we notate this by saying we find the divergence of F by taking our del dot operator, which means that I am going to go ahead and take the partials of each of these m, n, and p. So the partial of m with respect to x looks like this, plus the partial of n with respect to y looks like that. And the partial of p with respect to z looks like that. So that is what's considered doing del dot f. Now, in order to find my scalar result, we are calculating at a specific point, and that point is 2, 1, -1. So now that I have my del dot, I am going to go ahead and take and evaluate at that point. So I would get my first term like that. My second term, and my third. So like I said, this doesn't look like a traditional dot product, but dot product is at the heart of it because we are taking our vector field F and combining that idea of our gradient by taking the partials. Okay, that's the whole idea behind this thing. So it looks like I'm going to get -12 -4 -2, which is giving me -18. And since divergence is negative, I have more flowing in than out. So I would have a drain. Divergence is negative. So that would mean there is more fluid or energy or whatever. So more enters than leaves. Or if you want to put it simply, this would be a drain. Okay, and that's the idea of divergence. So again, just keep in mind, we are using that del dot operator. We want a scalar. We want to find if it's greater than, less than, or equal to 0. So then that leaves us with curl, our other way to describe a vector field. And curl is a little different. It is the measurement of the tendency of rotation of our vector field around a point. So I am at a point. What is the tendency for my physical body, I guess, to rotate at that point in the vector field? And we look at that as being either counterclockwise, clockwise, or no rotation whatsoever. So if curl is greater than 0, rotation is counterclockwise. If curl is less than 0, rotation is clockwise. And if curl is equal to 0, there is no rotation whatsoever. So one way that I always describe the idea of curl, again, I'm standing at some point in my region R. Here's the point right here. And I guess I could think of myself standing there, or I could think of I have something like a paddle wheel. And if you can picture a paddle wheel, it's like when you have the water generated energy and they have these kind of paddles in the water. Here, I'm going to try and give this a little bit of dimension in my drawing here. So Let's see, here's my paddle wheel. So let me do this arm of the paddle, that arm, and then there's like these other ones behind. So if I drop this paddle wheel at some point, this point specifically within region R, is that paddle going to rotate in a counterclockwise manner or a clockwise manner or not at all? Okay. And that's curl. So since we used dot product to find divergence, you could probably guess that to find curl, we are going to use the cross product. And again, that's the underlying idea. But like the last one, we are using another one of these mathematical operators. And this one, again, if you use a little inference here, is called del cross. And the idea being we are taking our gradient and we are crossing that with our vector field MNP. Now this one, we actually are going to do our cross product, okay? Now there is a shortcut and we'll kind of go through, by shortcut, I mean formula that you could apply when we go through and do this. So okay, to put it this way, we don't have to do cross product every time. So to go back and kind of correct what I said just a second ago, we don't have to do cross product every time. We are going to do it right now so that we can arrive at this kind of formulaic way of doing del cross. Okay. And then we'll apply it to the example that you see over there. So I'm going to go off to the side here where I have a little more room to do my cross product. And I'm going to go ahead and set up, I want to do the gradient with MNP. So in order to do my cross product here, I'm going to say for my components I, J, and K, I would be taking my gradient, so my partial with respect to X, my partial with respect to Y, and my partial with respect to Z. That would be my gradient. And I'm going to cross that with MNP, my vector field. So again, I won't go through the specifics of how to do our 3x3 cross product here. If you don't remember, that may be something to go back and review before our test for sure. But essentially I'm going to get I'm going to switch now to Lagrange notation because it's just going to be easier. Okay, when I go to do my 2x2 here and I multiply p by the partial with respect to y, then I'm getting partial p partial y. And when I do that with n partial z, I get n partial z, okay? So that's where those terms are coming from. And then I do the same thing with j here. So as I go to do my 2x2, it's telling me the function that I'm taking partial what variable? All right. So this, in effect, is going to be our formulaic way of finding curl. And you will see this where it essentially leaves out the I, J, and K part because you can you're kind of finding those components as you do each of these mini discriminants here. So you will see it written out. In order to find curl, you do py minus, or I'm sorry, p partial y minus n partial z minus p partial x minus m partial z plus k, oh, I'm sorry, leaving off the k, plus the quantity n partial x minus m partial y. I never found that to be something that I could just memorize. So that is given to you on the formula sheet. So you will have at least that one given to you on the formula sheet. And I think you can go back and check the one from Unit 2 test because I believe there was stuff with vector fields on that formula sheet. So you can check and make sure that I'm correct in saying that. So I'm just going to write that again here. Find the curl of this vector field as an example. In order to do that, like I said, we are going to take this and then we're going to go ahead and substitute in all of our partials here. All right, so keeping in mind, this is M, this is N, this is P. Okay. And we could go ahead and say this is my I component, this is my J component, this is my K component. But essentially what we get here is 0I, 0J, and 0K. So this would be an example of where this simplifies all the way to 0, and we get no curl at that for that vector field. And in fact, I didn't even pick a point for that one. Probably should have picked a point. It wouldn't have mattered, but generally that's what we do when we find curl. It's at a specific point. So that was a little bit of trickery there because I didn't even select a point for us to do because I knew the curl was going to go to 0. So that means it doesn't matter at what point you place your paddle wheel or whatever it is, that there's no curl at any point in this vector field because all of those canceled. Now, it doesn't mean that you couldn't have other vector fields that generally have curl, but not at specific points. That may be the case where we have some vector field and at certain given points, there is no curl, but at other points there is. So again, that's just, that's kind of how that works. So let me know if you have questions about this. This is the basic idea with divergence and curl. But as always, we'll kind of continue working with those ideas in class as well. Hope you have a great day.